would like to thank the organizers for inviting me. And my task today is to kick off this session, to give you kind of an overview of what we have found so far and not found so far. And I think Olivier gave like half of my talk, so my task is very short. Let me see if I can, there you go. So first of all, yes, there are 3 stars. These are the basic properties. In effective temperature, A and B, they bracket very nicely our sun. The major difference to our sun is actually almost only the stellar metallicity. They're significantly more metal-rich than our sun. The same we don't know about Proxima, because metallicities are very difficult to measure for M-dwarf stars. We have actually the best information about these stars when it comes to their masses and also their radii. We have already interferometrically measured radii for all 3 of these stars. And for the 2 solar-type stars, we also have dynamical masses. And the mass of Proxima is probably the least constrained of the 3 stars in the system. And the dynamical mass comes from a very nice 3D orbit that's possible nowadays. This was just published very recently by Pourbet and Beaufin. And the data that you see there are absolute radial velocities from Harps. This is the spectroscopic orbit. The line is the fit. And together with the visual orbit of Alpha Centauri, you get the masses and the parallax of these stars very, very precisely and accurate. And these data up here, these are actually data that I produced for my PhD more than 15 years ago that I was very happy to see are still useful for something. Another interesting aspect about Alpha Centauri is whether Proxima is actually gravitationally bound to the inner binary A and B. It's not clear. It's like right at the Hill sphere of the binary, and it will probably take a long time for us to really make the decision whether it is actually bound to the inner binary or just a common proper motion star. So the same data, this old data, more than 15 years ago, that I produced for my PhD, I actually used to calculate upper limits for masses. Here the data. They had a radial velocity precision of about 12 meters a second, which is, of course, pathetic for nowadays standards. But you could still use it to constrain the presence of giant planets. So that's what I did. And the lines are basically everything above the line we could rule out. We should have seen it even with these data at that time. And below, that was still possible. But the line was already around 1 Jupiter masses. So even back then, we could say there's probably not a Jupiter mass companion around either of the stars in A and B. So I'm sorry, James Cameron, the Avatar gas giant is probably not there. And now we know definitely it's not there. And the shaded area that you see here, these are dynamical limits. So you can combine the mass upper limits from radial velocities with dynamical limits that were calculated in 1907 already by Wiegert and Holman, and recently also by Lissau and Quarles, that showed that, of course, the gravitational perturbation by the other star make orbits unstable out to a certain range, and it's typically around 2.5 or 3 astronomical units. So that narrowed down already back then the possible range of planets in the system to down here. But what about small planets? Okay, gas giants, they are not there, but small planets. We are really in the best possible time at the moment because we now have this fantastic Kepler data. Natalie Batalha just sent this slide which is the latest numbers, the occurrence rates based on the 17 quarters of Kepler data. And you see the yellow lines indicate the effective temperature range of the 3 stars in the Alpha Centauri system. And in these bins, you see the frequency of planets in the size range 1 to 1.6 Earth radii, so more super-Earths than Earth-sized planets. They are large numbers, I mean, large uncertainties, but still, we are talking about 10, 20, 30, 40% in the habitable zone. The habitable zone is also indicated here. And down here would be Proxima. If we extrapolate this to even smaller sized planets, then the occurrence rates is even higher. But this is, of course, for single stars. We must not forget that Alpha Centauri AB is actually a very close, tight binary. The semi-major axis is just 23 astronomical units. The 2 stars get as close as 11 AU. So how did planet formation actually work in this system? The protoplanetary disk was certainly truncated, and the gravitational perturbation of the other star must have influenced the disk and the planetesimals in the disk. And as an observer, I say we are actually in the best possible situation because there are theoretical predictions that say, yes, it worked, and also others that say, no, it didn't work, so let's go and look. Let's perform the experiment to make the distinction of theoretical predictions that one said, yes, you can form planets, and this is one result of several simulations run by Guyon et al. Of forming rocky Earth-type planets in this truncated planetary disk around, in this case, Alpha Centauri b. And the other argument is that the perturbations causing from the second star would make the eccentricities of most planetesimals too large and impact velocities too high to allow constructive accretion. So they would grind themselves to dust. But this is planetesimal accretion. Maybe nowadays, with the Pebble accretion model, this would be anyway obsolete. But the point is that we have probably the technological capability now and in the coming years to actually make the experiment, the observations to confirm these theoretical models. I grew up as a spectroscopist, so I did this radio velocity observation. So let's talk a little bit about radio velocities of, can we detect small planets in the Alpha Centauri system by radio velocities, by the standard technique? Well, it's challenging. We are looking, of course, for the semi-amplitude of a radio velocity signal that's very, very small. For habitable zone planets around A and B, we're talking for an Earth mass still only of the order of 10 to 12 centimeters a second. So an order of magnitude, of course, below what even the best instrument nowadays can deliver. It gets better if we talk, of course, about more massive planets. A 10 Earth mass planet gets you actually already there to about a meter a second. But then a cosmic irony happened. Right at the time when teams were assembled, when spectrographs were built and became available, and even more importantly, funding agencies agreed to fund these projects. And there were in particular 3 projects, one at Harps, one at Chiron, and one at Hercules in New Zealand, that said, okay, to find these very low amplitude signals, we have to hit this star very hard, taking a very, very large number of observations. And right at that time, the cosmic irony was that the visual orbit of the star made them come together. And they are now as close as about 4 arc seconds. And when that, at such a close separation, here's an actual image of A and B, what you have is typically that light of the other star, unfortunately, enters the fiber and enters the spectrograph as well and cross-contaminates the spectra, and you cannot obtain your precise radial velocities anymore. In 2012, Xavier Demusque published a Nature paper showing the exquisite quality of the Harps observations of Alpha Centauri b. And I think the most astounding thing of these observations were the very, very clear identification of the stellar intrinsic signals. So Harps has such a high precision of maybe better than 1 meters a second, and they had about 450 data points, and they already got to the stellar astrophysical limit, showing that the magnetic activity that produces changes in granulation and, of course, spots, so that you get spot modulation, shows up in your data on very different timescales. So it showed up in long-term timescales of many years, akin to the magnetic solar cycle, to the spot cycle, but also in rotation modulation, where the strongest signal actually was present. And here on the right-hand side, we see this rotation modulation observed by Harps in some chromospheric lines very, very clearly. It's absolute beautiful data. And that made this analysis of this data set very complicated. And of course, most of you know that at the same time, they were hoping to have found a 3.24-day period small planet of about an Earth mass. And unfortunately, we think nowadays this was a false positive, again, probably introduced by the stellar activity signal of the star, folded with the observing cadence of the Harps observations. So we see that for precision radial velocities, if you want to find Earth mass planets, you have to characterize the stellar activity signal extremely well. But Xavier also sent me this plot, and this is a very, very impressive result too, because this shows when you have quality data like that of Harps, you can set those mass limits nowadays for planets in the habitable zone very, very low. Just look at the solid black line, which are the limits now, and we're talking now about Earth masses. And And right here is about the habitable zone for B, and you see down here we are at around 3 Earth masses. Then we have a larger peak, and this large peak here is, for instance, due to the stellar rotation period again. So we're getting there. We're only talking about a few Earth masses now in radial velocities. And Deborah Fisher sent me a similar plot for her Chiron program at CTIO, where she estimated the sensitivity or what kind of planets she can exclude from her data. And all the dark regions here she can already rule out. And here's about a year habitable zone, so it's a little bit higher, let's say Neptune mass or Uranus mass. And I was actually involved in the third project, in the one at New Zealand, and we had the worst seeing of these 3 programs. So we suffered from this contamination, really the most extreme. We tried to develop a correction method for this, which we were kind of semi-successful, but we are still working on it, actually. But what I did was that the reason that we were hoping to find these small planets with the New Zealand program is just the sheer number of observations. For B, we have 17,000 spectra. And these plots show you, by injecting a signal, what I was hoping to find by combining this with the stellar noise that we knew from the Harps data. And it shows it's actually very challenging. These are different levels of precision, 1, 2, 3, 4 meters a second. Even with this number of measurements, you're very, very limited by the stellar noise in your data. because I added this also to the data. And even with 1 meter a second, okay, you can see at this period, I injected the signal of a super Earth, free Earth masses. And it's detectable at the Harps level, but at lower levels of maybe 3 or 4 meters a second, it becomes not really detectable. One thing I want to mention, which is not radio velocities, the Harps result motivated a search for the transit of this 3.24 planet candidate. And they couldn't find it, but they found a single transit in the data in 2013, a possible single transit with a depth of about 90 parts per million, which would be an Earth-sized planet. And they could put some loose constraints, Bryce Demery, in 2015 on the period, which was somewhere less than 12 days. So that's, I think, worth mentioning. Now let's talk quickly about the small star in that system, Proxima Cen. I was involved in a campaign to observe this star with the ESO-VLT and UVES for 7 years. Here's our data. We got to about 3 meters a second. And similar to Alpha Cen, I produced a plot with upper mass limits. And as you can see, because the star is so low mass, we can, an amplitude of a few meters a second represents already something like a 2 Earth mass planet. So in the very close inhabitable zone, of course, of this M5 star, we get down to about 2 to 3 Earth masses already. I want to mention the pale red dot project. That's a campaign that was also targeting Proxima with Harps in combination with simultaneous photometry. And they just completed their data collection efforts. And they took basically a Harps spectrum of Proxima every night for quite a substantial number of nights. So this was another intensive campaign on Proxima. And I know I'm not directly involved in this project, but I'm a little bit involved, and I know that they're looking at the data, and they will present their results very soon, so stay tuned. So when it comes to radio velocity campaigns of these stars, I think it is important that how to move forward is to better understand the stars. Of course, it helps to improve the radio velocity precision. Maybe for AB, it would even be a smart idea to have an AO system now, to go through the years until the separation goes wider again. Also use a multi-wavelength approach. A near-infrared spectrograph would be very helpful so that we can disentangle possible activity and planetary signals. And since I also want to mention what's now coming next after my talk, is in order to really well characterize the activity cycles of Alpha Centauri. There's a great program at Chandra that will be the next talk. And then beyond RV, of course, what we really want to do is we want to throw everything at Alpha Cen. We want to do astrometry, we want to do direct imaging. And this is just an example. There's much more going on, but these are examples of what's currently done at Magellan with the Magellan AO or with SPHERE at ESO. Thank you very much.
Questions?
I went too long.
A comment, but I hate it when people do that at talks. So I think that, we've been working to try and figure out, starting last summer, when we all came together for the EPRV conference, why it is that we're stuck at a meter per second precision. And it's clear that we're looking at the stellar photospheric velocities. It's also clear that the stellar photospheric velocities are not imprinted in the spectrum in the same way that a Doppler shift is. And so that leads one to then say, well, if you have high enough resolution and high enough signal to noise, then maybe you can begin to separate them out. So we've been doing studies with Xavier, Eric Ford, my team, doing PCA analysis to see what it would take. And if you get to a signal to noise, which is ridiculously high, it's about 300, above 300, resolution above 300,000, signal to noise above 500, going towards 1,000, then in the PCA components, you can separate out the Doppler shift and the photospheric plage or spots. There are only 3 stars in the sky that you would ever want to build a spectrograph to do that for. One of them is Alpha Cent A, one's Alpha Cent B, and the third one is the sun. So you observe the sun, as Xavier is doing with Harps North during the daytime, and recover the signal from Venus to prove that you can believe your velocities, and then apply that to Alpha Cent A and B. So I think that this is a project that, behind an AO system, as you suggest, Michael, would be really cool.
No, I fully agree, and that's exactly what I meant here. That it has to be also that we really understand what these stars are showing us in terms of velocity fields and how we disentangle this from the Keplerian signal. And I think the near-infrared might help us too, because we can, it makes a difference if we are, yeah, sure, tellurics are a problem, but we do this for young stars already, showing if the Keplerian signal shows up in the near-infrared too, yeah.
We'll take one more question while the next speaker is coming.
Thanks for the nice talk. A comment and a question. So with regards to the occurrence rates that you showed that are coming out of Kepler,
Those are yours.
Yeah, well, they are, yes. But I just wanted to point out that the radius range that I used in those calculations is 1 Earth radius up to 1.6. That's where we have sensitivity. But if you're willing to consider a planet as small as Mars, for example, you're going to effectively double the area of the bin and therefore double the occurrence rate if you assume that occurrence rates are basically flat, which I think is a conservative estimate. And so when you do that, you end up getting, if I take a weighted mean of those numbers across all spectral types, I end up getting something like 0.15. So the average number of planets per star is about 0.15. But if you widen the bin in radius, you get something like 30%. The fact that you have multiple stars in the system means that you have a greater than 50% chance of finding a small planet, rocky planet, in the habitable zone of Alpha Cent. This, to me, is tremendously exciting and makes Alpha Cent a great opportunity. But my question for you is, given the sensitivity curves that you've showed, you flashed up, and I didn't get to parse them quickly enough, and from the existing radial velocity surveys, is there any region of parameter space that's we know planets do not exist, where we also know the occurrence rate is actually pretty high?
Like the first 80 days.
Like maybe, short periods or short word of 100 days maybe, and
so these are the tightest,
smaller than 3 Earth radius, for example.
Yeah. So as you can see, in the region where Kepler is most sensitive and has the best numbers, it's below 2 Earth masses, going down to 1. So. Below
2 Earth masses. Yeah. Okay, those are pretty tiny planets within 100 days, and those are, that's a part of parameter space where Kepler finds planets are pretty common. Of course, the concern on our mind is, could the occurrence rates for multi-star systems be different than for single-star populations? That's one of the things we're thinking.
Yeah, I think one thing that we should bear in mind with these kind of simulations, okay, Xavier might correct me with this, but this assumes several things, and one of the things that it usually assumes when I do it is a single planet system. If you have a multiplanetary system, and that's very hard to simulate for injection and recovery methods, the signal gets way more complicated, and you could miss, multiple more massive planets than this.
Good point. Thank you.
Thank you.